So hi, my name is Matheus Sphere, and in this video I'm gonna be showing my assignment 3 of machine learning. So in the first part here we are just importing some libraries. Some of them are gonna be responsible for plotting the image, for filtering, for charts, to convert an image in binary code, and so on. So here we are downloaded the image from the internet, and then we are converting in so this format is not like a human readable format. The machine can do it, but then we can convert back using those commands, and then we can see here the image. So you see we are calling the matplotlib library, and then here we can have the same image to see how it looks. And then here we are checking if the image is RGB or no. So for example, here we are checking the three color channels, right? You have the 0, 1, and 2, with the RGB, red, green, and blue. So if it shows false, it means that they are actually different, so we have RGB. And then we are removing that from here. So now it's only 2D. We are not using 3D anymore. So we do not have the 3 dimensions anymore, the height, the length, and the color channels. Now we have only the height and the length. And then after removing the RGB colors, we can plot here how it's looking now. And since we don't have the RGB, it's just grayscale. So it goes from white through all the levels up until it gets black. And then in this part here, we pad the image, we define the kernel, and then apply convolution by sliding the kernel across the image. So because here is also rounded off 0 and there is 1 in the center, it's going to be scanning the image and it's going to do the math and show the sum that is going to be very similar to the original one, because the kernel is pretty much just a 1 in the center. And then it's going to just be an identity filter. So first we define a better function to ensure the pixels are going to stay between 0 and 255. Then we define a convolution function that takes the image and kernel as input. We apply padding to the image to handle edges, determine the kernel size, and create the output array. Next, we iterate over the image, extract local regions matching the kernel size, and apply convolution by multiplying and summing the values. Optionally, we clip the output values to maintain valid pixels intensities, and finally return the transformed image. In this step, we use convolution kernel to detect horizontal lines in the image. The kernel has positive values in the center row and negative values in the top and bottom rows, which helps highlight horizontal edges when we apply the kernel using the convolution function. Areas with strong horizontal chains become bright, while other regions become dark. The result is an image where horizontal lines are clearly visible. Now answering the question. In this step, we create a convolution kernel to detect lines at a 45-degree angle. The kernel is designed so the positive values align along the diagonal direction and negative values in the opposite direction. This allows the filter to highlight edges that follow a 45 degrees orientation. We then apply this kernel to the image using a convolution function, and the result shows bright lines where 45 degrees edges are present, while other areas remain dark. In this step, we create a convolution kernel to detect lines at 135 degrees angle. This kernel is designed by reversing the diagonal pattern using the 45-degree kernel. Positive values are placed along the opposite diagonal, while negative values are placed on the other side. This allows the filter to highlight edges that are oriented at 135 degrees after applying the kernel using convolution. The output image shows bright lines where 135 degrees edges are present, while other regions remain dark. And then we apply an edge detection kernel to the image. The kernel contains positive values on one diagonal and negative values on the opposite diagonal. This structure allows the filter to detect changes in intensity along the direction. When the kernel is applied using convolution, edges where there in a strong contrast become visible as bright lines, while uniform regions remain dark. Answering to B. This kernel detects edges by comparing each pixel with its neighbors. Large differences produce bright values, highlighting the contours of the object in the image. And to see, this kernel detects edges by comparing each pixel with all its neighbors. It produces stronger and sharper edges than the previous kernel because it considers diagonal difference as well. Okay, so part B. This part imports required libraries, loads the CIFAR10 dataset, converts labels using one-hot encoding, and normalizes image data to improve model performance. A CNN model is built using COMP3132 for feature extraction, max pooling for downsampling, flatten to convert data, and dense layers for classification. The model is compiled using ADAN optimizer and category cross autopilot laws. A custom callback is created to log training validation accuracy every few epochs. The model is trained using model fit with specified epochs, batch size, validation data, and callback. So in this case, epoch is 10, so we have here the 10 epochs that were ran. So this part plots the model performance over time. The blue line shows training accuracy, and the red dashed line shows validation accuracy. The x-axis represents epochs, and let me go down here. Sorry, the x represents epochs, and the y represents accuracy. As epochs increase, both accuracies improve, meaning that the model is learning. The gap between the two lines helps us to check if the model is overfitting. Question 6. I added one more convolutional layer and another max pooling layer to make the model deeper. This allows the model to learn more complex features from the image. After training again, the performance improved because the model can extract more detailed patterns. And then we can see again, we're running 10 more epochs. And here's the chart again, so we can see the training accuracy, the blue line, and the validation accuracy, there is the red accuracy and epochs. So question 7. The bigger model performs better because it has more layers, so it can learn more complex features from the image. This usually results in a higher accuracy compared to the original model. However, the bigger model also takes more time to train and has a higher risk of overfitting. So question 8. In this part I added the dropout layer with a value of 0.5 after the flattened layer. Dropout randomly disables some neurons during training, which helps prevent overfitting and improves generalization. After training the model again, we can see that both training and validation accuracy improved. The validation accuracy is more stable, which indicates the overfitting has been reduced compared to the previous model. And here we are plotting the charts. So in the graphs, both training and validation accuracy increase over time, and the gap between them is smaller. The loss is also decreasing steadily. This shows that the model is learning well and generalizing better with dropout layer. And then question 9. A dropout layer is used to reduce overfitting. It works by randomly turning off some neurons during training, so the model doesn't rely too much on specific neurons. Because of this, the model learns more general patterns and performs better on a new data. So yeah, that's the end of my presentation. I hope everything is clear.